Good afternoon. Welcome to the final talk of our workshop. This is the third lecture of Giovanni Italiano, who will continue speaking about building hyperbolic manifolds from Coxeter polyhedra.
Okay, does the microphone work? Yeah. So before we start, let's take the time to appreciate the work that the organizer did to organize this conference and workshop and thank them for these beautiful 2 weeks. Okay, so the objective of today, as anticipated, is to try and explain all the techniques that we need to construct. This is bad chalk. Is there? An example of a 5-manifold H hyperbolic, complete and finite volume, which fibers so know by a very famous theorem of Hegel, all hyperbolic closed 3 manifolds virtually fiber, so they have a finite cover that is a fiber bundle over a circle, but until like last few years, it was no example known in higher dimension, and we went to dimension 5 because the Euler characteristic is an obstruction to fibering in even dimension, because fibering implies that the Euler characteristic of the manifold is 0. But as I told you last time, in even dimension for hyperbolic manifolds, the Euler characteristic is actually some constant depending on the dimension times the volume, the hyperbolic volume. So it's never 0. Okay, and the techniques that we are going to use are to find an explicit hyperbolic 5-manifold, and from this build a map to S1, and then study this map with some tools that I'm going to. So the idea is that you can build hyperbolic manifolds from a right-angled this is a summary of last time, a right-angled hyperbolic polytope plus a coloring of its facet. So this coloring encodes the way you build a manifold starting from a polytope, and one very nice property was that the manifold is tessellated in copies of the polytope, and the dual of the tessellation is a cube complex. And cube complexes are very nice and simple and easy to study and do construction on. So this is already promising because we have a reasonable way to study the manifold. There's many techniques that can apply. So the last thing we said is that with this cube complex, what we want to do is to first define the map to S1 on the one skeleton. And to do that, our objective was to draw arrows on every edge of the cube complex, which is what we call an orientation, which is just drawing one arrow for every edge of every cube in the cube complex. And I told you I really like coherent orientation, which are that orientations such that every time we have a square, parallel edges have parallel arrows. So this is not a torus. It's just a square with some arrows drawn on. And yes, and the nice thing of coherent orientations is that you can build a very nice diagonal map to S1, which is just identifying every cube with the standard cube in Rn, if I take an n cube, and then sending every point of the n cube to the sum of the coordinates, and then project into mod z, getting S1. And what I told you is this map is just the diagonal map. We are just taking the source and the sink, and we are basically going diagonally. So these are the level sets of S1, and if we want to look at the flow lines, they're going like this. These are the flow lines of if you follow S1. Okay. So this is like the state of the art as last talk. What I want to do is now try and find. So this is just a map of S1. We need to study and understand it because not most of the map of S1 that we can build with these techniques will be horrible and not very nice. We want a very nice map to S1. Namely one that doesn't have any critical point. So we will have to do some work to find a nice map. And to do that, we want to make the combinatorics of the polytopes and this construction talk. So we will have a way to encode what these arrows are on the polytope. So I'll draw this same example as we were drawing yesterday with the hexagon with two colors. Just to have a simple example that can be drawn. So it's an hexagon drawn in red and white. Right-angled hexagon in the hyperbolic plane. So this coloring encodes the attachment, where I say that I glue horizontally when I cross white, and I glue vertically when I cross red. So for example, this one is glued to this one, and this one is glued to this one. And okay, so the dual cube complex is just taking a vertex in every hexagon, an edge for every edge of an hexagon in the tessellation, and for every vertex we take a square, because it's just two-dimensional. So for example, in the tessellation, this edge is the same as this edge. So in the dual cube complex, there's an edge that connects this to this. Now, what does it mean putting an arrow on this edge? Putting an arrow on this edge just means that if, for example, I choose this arrow, then here is going like this because it's the same edge, it's the same arrow. So one way to encode this on the polytope is simply writing O here and I here, which means here the arrow goes out, here the arrow goes in. Okay, so maybe this other is another edge, and if I put an arrow like this is an in, this is wrong, and this is an out. Okay, so let's put a definition. A state is an assignment. So a state is something that is on the polytope P of a label that I call status, which can be in or out to each facet. So when a polytope has a state, which I may draw like this, I don't know, just random stuff, what is happening in the dual cube complex is just I'm deciding what the arrows are going to be in this vertex of the cube complex. So a state is just deciding an orientation on one vertex, around one vertex. Okay, and now I want to define the orientation on the whole cube complex. And I also want it to be I want it to be, first of all, an actual orientation. I don't want to put, I cannot put just random states on all the polytopes because, as I told you, this edge is also here. And so if here we have an out, here we have an in. So first of all, I need to have something that is well defined, and then if I have the luxury to do so, I also want something that's coherent, so something that works in dimension 2. So what I'm going to do in general, which is easier to encode combinatorially, this combination is just to choose one state for one polytope, the polytope P00, for example, and then propagate this state to all the other polytopes while making sure that this keeps getting well defined. So how do I do this? Here comes another combinatorial definition, which is the one of a system of moves. So a system of moves is just a very fancy name to say something that's very simple, is just a partition of the facets in some subsets that I called moves. So these are just subsets of the facet, such that facets that have the same color are in the same move. So such that same color, same move. So if you want, you just can say that this is just a regroupment of the colorings. I just choose what colors are in what move. And maybe a very easy system of moves is just the coloring. The coloring is a system of moves. And I say that a system of moves is sparse. A system of moves is sparse if it has the same properties as the coloring has. So if when the facets are adjacent, they're in different moves. So if adjacent facets are in different moves, so why do I need to rename all these things? What's the point of this definition? Is just that, so a state is something that I will have on one polytope. I will design an initial state on this polytope, and then a system of moves is something that propagates the state. So let's say that the system of moves here is just that white is one move and red is another move. How do I propagate this state? The condition is very straightforward. When I move from this polytope to this one, I cross a white facet. It can be this one, or this one. They all go here. And the moves prescribe how I change the state. How they change the state? When I cross one facet, I change all the statuses of the facets that are in that move, and I just keep the others the same. So for example, when I cross white, I change all the white statuses, and I keep the red the same. So this is a new state when I cross white. When I cross red, I change all the red ones, and I keep the white the same. And when I cross and go, yeah, this is an I. Is it all? Yeah. When I cross and go here, I could just see it maybe crossing from here to here, or from here to here, and the result is the same. I just, for example, take here and cross red, and cross white, sorry, and so I get I, O, and then get O, O, I. So propagating along a system of moves just means that the moves prescribe what statuses change and what not. And so this gives me all the arrows. And then there's, so the fact that the system, that the orientation is well defined is just by the definition of moves, because when I cross one color, then I change everything that I have to change because the color is all in the same move. And the definition of coherent, so having these nice squares here, depends on the fact whether the coloring, the system of moves is sparse or not. So sparse system of moves give coherent orientation. And this is actually an if and only if, because when it happens that two facets are in the same move, then I'll have a square along the ridge that is not coherent when I go there. But like you can check it for yourself if you want to see that. Otherwise, you can just trust me. So okay, what's the entire? So for the moment, let's say that we just managed to find a sparse system of moves. For example, we just choose the coloring, and now we want to understand the map in some sense. So what do we do? So for how we build the map, everything glues perfectly well every time we glue. So the point is this: why the map can be not regular. The map can have singular points because we are defining it on every cube and then gluing everything together. So in every cube, everything is fine. But when we glue, maybe we introduce some singularities. And every time we are gluing something that's dimension at least 1, then we'll have a direction on which everything flows, because on the edges, it will really be coherent on this. The only problem is when we are gluing around points, we will have we can have some singularities along the vertices. So the point is, in some sense, so the issue, so this is a well-defined map, what we want to study, and like if it was a Morse function, this is actually an equivalent, sort of PL equivalent of a Morse function. And we have the vertices of the cube complexes that are 2 to the power of the number of coloring that are potentially so just to make 2 examples, I'll take, for example, let's say something like this. Let's say that the polytope is just a square. We're maybe building a torus, and we're trying to build some maps. And then on a square, we have a status, which is I-I-O-O. How does a point here, the dual to the square, how does the map behave here? We'll have a point, which is in the dual the square. Then we'll have the edges. And then the arrows are going in here and are going out here. And if you look at the diagonal map, the diagonal map is going like this. Here, it's going like this. Here, it's going like this. Here, and it's going like this on this square. So the flow, if you want to follow the flow of S1, is going like this. So this is a saddle point. As a Morse function in dimension 2, no? This behaves like a saddle point. If, for example, I have, let's do an example with an hexagon, maybe maybe I just chose this, then what happens here? So as always, we have a point that's here. We have the edges that go around. This picture is just bigger. In, the arrow is going in. Out, the arrow is going out. And in this square, the diagonal map is going like this. Now the flow is vertical. These are the level sets. On this square, the map to S1 is just growing like this. On this square is growing like this. It's just, so the flow here is just going up. You follow the diagonal map, you just go up, and there's no critical point. This is not a critical point. So what's the? So here, like the coloring defines the manifold, but locally the cube complex. Now I'm studying the cube complex locally, no? And so locally, I don't care where these arrows will go. Just locally, they're inside, and I'm looking at how the map is defined just locally around this point. So the coloring plays no role in this. Was that the question?
Yeah, but if there were a coloring, this would, I mean, that's compatible with mapping. It would give a map to.
Yeah, the point is, you're asking me, like, if I put a coloring here, what's going to happen? Like, this is not a critical point. When I put a coloring here, maybe the one with the opposite colors, when I cross, let's say I cross this bold color, what's going to happen? It's going to happen that this is bold, this is bold, this is bold. The one in the bold coloring are going to change, and so they become in, out, out, and this becomes in, out, out, because they're staying still. And now, if you look at this, the arrow here, let's do it like here. Okay, let's just make a big point here. Here the arrows go in, and here the arrow go out. And if you follow this, you get a saddle points as well. So you will get something that goes like this. I don't know, like something like this, no? And then so this is going to be a saddle. So you can get, so in this case, you will get 2 points that are just regular, and then you get 2 saddle points. And then, actually, when you do, when you build a Genius 2 surface, then you will need to have like some, for all their characteristic restraint, this will, each of those will contribute 1 to the other characteristic, and then -1 to the other characteristic, and then the sum gets. You could also maybe put everything out, and you just will have a source as a critical point, and then you follow, and you can build many maps. This is okay. So the point is, we want to understand what happens at the vertices, and why some critical points are bad and why some are good. And the point here is that you look at the link of a point, and you look, so what does this point see around itself? It sees this hexagon. So you're basically taking the dual of the dual, so you get the same. And so here, what's the nice part is that here the part that goes in and the part that go out are both simply connected. They are both like collapsible. They're you can think of it as like they're just a point homotopically. No, there's nothing funny happening. But here, the part that goes in is not collapsible. It's not even connected. And here, the part that goes out as well. And the same happens here. So the point is, when you look at the link of the point sees the polytope, and sees the polytope with some ins and some outs. And these ins and outs are describing what happens to the map. So let's say this more precisely. So how do we say it? So a vertex of the cube complex has a link around itself. It's just the link of the vertex of the cube complex, which is P. And so with this, we will call it link of V. And subsets of this link, we have, there's link up of V, a link down of V. This is just as a subset of the link is the facet of P, the closed facet of P, such that the status is out, and this is just the same as the status is in. And this ascending and descending links are precisely what the ascending and descending links are for normal differential Morse function. So it's just something that define you what part is going up and what part is going down, and how the fiber changes when you cross the critical point. So the point here is to understand these links, to understand the map locally, and then you can say something about the map globally. So let's state a theorem without. So there's this whole theory of Morse function for there's a whole theory of Morse functions for cube complex and affine complex in general, and there's a beautiful paper from Besvina and Brady, which analyze this kind of maps and tell you what happens in function of depending on what the links are. So if you have a map, let's call F a map from an affine complex, for example, a cube complex, to S1, be a map which behaves like this, so like an affine map from the cube complex to S1, which has some properties which are satisfied in this case to be actually a Morse map. Let's say take all the links up and links down of every vertex of the cube complex. Then let's put it like this. I'll add some other things before, so just to. So the point, if all links, ascending and descending links, are collapsible, which is a notion of contractible. It's a bit stronger for complexes. If all the links are collapsible, then there's no critical points. The map F is a fibration. We actually get something. So this is a very, very strong condition. Now you will have so many simplicial complexes. There are 2 to the power of the number of colors. You have to have them all be collapsible. Maybe you cannot do that, and you have they build this theorem to actually have some examples in group theory, and so they also cared about weaker hypotheses and hypotheses on the groups. And so the point is if all links are connected, then if I take the map at the level of pi ones, this has finitely generated kernel, which is something that's sometimes called an algebraic fibration of the group pi 1 of C. And then if you strengthen this condition on the links, you get a stronger condition on some. For example, if all the links are simply connected, then this map here has finitely presented kernel. So depending on what you want, there's different versions of this theory that give you something. In some sense, when the links are connected, you are not attaching anything that resembles a one handle. When they're simply connected, you're not attaching anything that resembles a two handle. So you're not ending relations in the group in some sense. So these are, and when they are collapsible, they're k-connected for every k, so you're not attaching handles at all. You're just, if you want to keep the parallel with the Morse theory, this is the conditions. So, okay, I do try and do one example of something that works, and then we'll do a small break. So I can take the right angle ideal, the right angle ideal octahedron in H3, and color it with a checkerboard pattern. So we just color this first with red, this one with red, the one back in the top with red, and this one here down left with red. And this gives me a hyperbolic tree manifold, which is tessellated into 4 copies, 2 to the power of 2 of this octahedron. It will have 6 cusps, 1 for each vertex. If you track it down, they just keep being 6. And I want to, so what's the issue? Maybe I should say that this combinatorial description of this, let's site, there's Jankiewicz, Norin, and Weiss. They gave this description as a combinatorial game, or at least a version of it. With description of the combinator of like building a construction that builds a map, like I told you, with states and moves. So we have there this. We want to do this construction on this and see the example. So since the octahedron is a bit complicated to see where I put the labels on, because like they're facet behind, and if I start putting labels everywhere, we'll stop understanding. I will encode everything on the dual of the octahedron instead of the octahedron. So the dual of the octahedron is a cube. So we'll draw So when I draw this picture, I just mean this. And this vertex here is this facet down here. This vertex here is this face up here. This vertex on the left is the face up left. Up back is the facet up back, and so on and so forth. Okay, and so the coloring here, and the edges determine the adjacency of the facets. And I don't put squares here. This is, in some sense, the fact that these vertices are not here, because this is ideal. So the coloring is this one. Now we're coloring this front top with red, and also back top with red. And we're coloring also the one on the sides in the bottom with red, and the other is white. And you can see it's the coloring because they never touch when they are. Okay, now what do I have to do? I have to choose a system of moves and an initial state. And before doing that, I'll just draw 4 squares, which represent the 4 octahedrons. Maybe and the last one. Okay, and maybe I just keep the coloring just so that we can remember and not get confused. So these, they draw like this, are actually 4 octahedrons, 4 octahedra that are there in the gluing. And now I have to choose a system of moves, and since I want coherent orientation, because I didn't tell you anything about what we do if the orientation is not coherent, I am forced to choose the coloring as a system of moves. So system of moves is the coloring, in this case. So white with white and red with red. And now I have to put an initial state on something. And if I want the map to be a fibration, then I have to start with collapsible, so contractible, if you want these links at the beginning. So maybe I can start, let's try this one. Let's say I, out, 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 out. So let's see the links in the cube, and then we'll try to imagine ones on the octahedron and see it's exactly the same, at least it's homotopically equivalent, and then we'll just look at them in the cube. So what's the link, the ascending link here? It's just the subcomplex generated by all the eyes. And this is just this, and this. So it's just 3 segments glued together. This is just. And all the outs are the same, are just 3 segments glued together. If you want to look here, maybe I'll draw another octahedron, because otherwise, how do I do this? Why am I? This is, no. Oh. Let's. So what are the facets that are illuminated with out here? Are this one, this one, this one, and the one back in the back. So it's the same sort of snake, just a bit thickened. Okay. So here, at the starting point, we're just choosing collapsible links, so nothing bad happened. And what happens when we propagate? When we propagate, let's say that as before, white is going horizontally and red is going vertically. What happens when I change white? I get out, out, in, and I get in, out, in, out. Okay, and the ascending and descending link. The ascending link is just the subcomplex spanned by all the vertices with eyes. So it's this one, already a 3 segment, and the out is this one. So they've changed, but they're still the same. And if I just follow everything in this picture, I will get out, 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 in, and then the picture is still the same. Those 3 segments, and here, if I look at this, I just get out, out, no, the opposite, in, and then I get out, 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 and it's the same. No, it's just this one, and this one, and then this one, and this one. Okay, so the issue here, if we are lucky to find something that works, this is a sort of, this is the combinatorial game. We are choosing an initial state, we are choosing everything. No, we are choosing the coloring, we are choosing the initial state, we are choosing the system of moves. And then we are just following an algorithm, generating all these ascending and descending links. And if we were smart at the beginning in choosing the things just right, then the links link down are all collapsible. And then the map F from the cube complex, dual cube complex to S1 is a fibration. So here there's a big, small issue. I have the map on the cube complex and not on the tessellation on the manifold, no? And this is not a problem at all when the manifold is compact. Because when the manifold is compact, the cube complex and the tessellation are just the same, the 2 different descriptions of the same manifold. And so we are done. When the manifold is not compact, then they're a bit different. Because, for example, the cube complex, since here there are no vertices, in the cube complex there will be nothing that's 3-dimensional. And so the cube complex is only 2-dimensional, cannot be diffeomorphic to the manifold. Since it's 2-dimensional, the manifold is 3-dimensional. So when there are cusps, when there are ideal vertices and then so cusps, C, the cube complex, is only a spine of the manifold, is only homotopically equivalent to M and not diffeomorphic, so we are not completely done. But this is just a technical thing that you can avoid by doing something like truncating along a cusp, truncating the polytope along all the ideal vertices. So here we have a square. And then leaving those new facets uncolored. When you build everything, these facets will form the boundary, which is the cusp section. And then you will have to play the game on the polytope and checking that all the links are nice, and then also on the cusps, and checking that also all the cusp fiber. And if this happens, then it's good. But the cusps are going to be much easier than the manifold, because if you, most of the time when you build manifolds like this, if you don't do things that are too weird, you just get toruses, and it's very easy to get toruses, to tori to fiber. So okay, I think I'll stop here for having a small break, maybe 10 minutes, and then we'll start again. Does someone have any question in the meantime? Okay. Yeah, okay. So I told you maybe yesterday or one of the previous lecture, I told you that there are examples of hyperbolic right-angled polytopes only up to dimension 8. And now I'm going to talk to you, I'm going to tell you about these examples. So there's this beautiful family of polytopes, which goes, depending on what's your philosophy on, and I'll say from dimension 3 to dimension 8. You can also say from dimension, let's put it as the next point. There's an equivalent dimension 2, maybe even 1 if you want to count the segment as a polytope. So there's this family of polytopes that exist in dimension from, let's say, 2 to 8, let's say, or 3 to 8 if you prefer to build. And it is very symmetric. These are, for example, they're dual to the so-called Gaussian polytope. So their duals are sort of these semi-regular polytopes that were discovered by Gaussian in the 1900. Gaussian was not even a mathematician; he was a lawyer that had no clients right after graduating, and started looking for semi-regular polytopes, and he found many. So this. And these are, I'll tell you the number of facets just to give you a flavor of this. Like P3 is 3, P4, 6, P5, yeah, 6, 10, yeah. I started with 2. Yes, this is 16. This is 27, I guess 56, and 120. So they get very big in the end, but P5 is still very reasonable. For example, P5 as, if you look at ideal vertices and real vertices, P5 as 10 ideal and 16 real vertices. So it's still pretty small. If you look at P3, we can draw it since it's three-dimensional. It's just a triangular bipyramid. So it's just this. Here, it has 2 ideal vertices and 3 real ones. So the 2 ideals are those 2. The opposite is the opposite. I'm sleeping. Yeah, so it's real vertices, ideal, I wrote it. So, yeah. Yeah. So I'll draw a square on the ideals. I'm sleeping still. Okay. But if you look at P8, then it has an insane number. So just the cusps are like, I think, these numbers, and the real vertices are like 17,000. So it's like a very big polytope. It's very hard to study. Here we have like 72 and 27, and et cetera, et cetera. I don't, yeah, 5, 5. I don't. So the point is they do exist, and I will tell you a little bit on how they're constructed and what's the why they are so symmetric. So the idea of the construction is very simple. It was actually in one of the exercises yesterday. So in every dimension up until 8, there is a Coxeter simplex, which is has a diagram like this. So let's do a 6-dimensional one. So there is a Coxeter simplex which this diagram that has the vertex that's opposed to this facet. So let's mark this facet with an X. Vertex opposed to X is real. And I remind you what this Coxeter diagram means. It means here the vertices are all, this is a 6-dimensional simplex, so it has 7 facets. And the 7 facets are represented by the vertices. All facet meets in a simplex. Every time 2 vertices do not have an edge connecting them, they have angle pi over 2. Every time there's an edge without a label on, this means the angle is pi over 3. And this only edge has angle pi over 4. And the nice property of this simplex is that this facet that I label with an X has angle pi over 4 or pi over 2 with all the other facets. So now I draw this picture in dimension 3 because I'm not yet able to draw in dimension 4. Let's draw a simplex. Let's say that this is our favorite face labeled with an X, and this is the opposite vertex that's real. This simplex tessellates the hyperbolic space. And so around this vertex, there are many of these simplex in the tessellation. And if we just take the star of this vertex and we get another polytope that's some of these simplices glued together. And what does this property with the angles do? What it does is when we are gluing angles between facets, we are either gluing either pi over 4 or pi over 2 angles with each other. So when two facets, when we are taking one, let's do a section, we are taking, this is maybe seen from above. Now this is the facet that we see. If the angle, if we're mirroring and taking something that's pi over 2, these two facets glue into one another and there's no angle anymore. When we have pi over 4 and we take something, and well, this is pi over 4 and this is pi over 4, and therefore the angle is just pi over 2. So taking the star of the simplex just give you a right angle polytope. And since the construction is so symmetric, then the polytope inherits all the symmetries that the link of this vertex has in the tessellation. And so we get some polytopes that are both right angled and very symmetric and also very small. They've been used also by other people. For example, let's just say one, Radcliffe and Chance use P6 to build the smallest possible hyperbolic 6 manifold with cusps. They build one with Euler characteristic 1. And they also build, first they built some that were orientable, non-orientable, and then also some that are orientable. And also the smallest known hyperbolic 5 manifold was been built this way. We don't have estimates in like in even dimension when we are in odd dimension, but the smallest known is this. And in fact, our manifold that we build, that will fiber, is going to be built with P5. It's going to be, the first one is going to be very much bigger than the smallest one. The smallest known hyperbolic 5 manifold is built with 2 copies of P5. We are going to do the coloring construction, and we cannot do it with only 2 colors. But after doing the construction, we can actually quotient down the manifold and build the same smallest volume known, smallest known 5 manifolds, still keeping the fibering structure in it. But we will not do this now. So the point is, let's describe P5 just for the flavor. And so the catch, not the catch, the takeaway from this construction in some sense is that all we care about is the adjacency of the facets. So I will not draw P5 because it's insane to even think of, but I will draw the adjacency, or at least I will describe the adjacency of its facets, which is very symmetric, and it's just, so I draw, it has 16 facets, so I draw 16 vertices, and I will put them in a hypercube. I will draw a small cube here. It's already too much. And then I will draw all the edges of the hypercube. And then I will tell you this is not the adjacency graph of P5 because here every edge is connected to only 4, and in P5 every edge is connected to actually 10. So what are the other edges that I'm not drawing because otherwise it's too many edges? The edges are all this plus the diagonals of the squares. Are also edges. So it's very symmetric. It's just this graph, but you have to think an edge is when it's connected by length 2. And when you look at this like this, there's an easy way to find an 8 coloring. To have a coloring, you need to have vertices of the same color not touch. And there's 8 coloring means we are dividing the 16 vertices here in 8 pairs. And very simple and very symmetric pairs are just taking one vertex and the opposite in the hypercube. So this one is with this, and let's do only one more and then I'll stop. Let's say this one with this, etc., etc. Okay, and then as before, you try and find a very symmetric initial state, and maybe at the beginning, what we tried at the beginning is just taking the system of moves that's just the coloring, and hope that that this works with some initial state, and then we realized that this is not possible. But just to point out, the difficulty here is that you have choice only on one, and then the procedure will generate to you 2 to the power of 8, which is 256, which is a lot, and all of this 256 actually times 2, because there's both ascending and descending, all these 500 need to be collapsible, which is a very strong condition. So what we realize is that this the system of moves, the trivial system of moves, cannot work. And for example, one way to see it is it just doesn't work on all caps. It's impossible to make it work on all the caps simultaneously. And so we were forced to consider this generalization of the Jankovic-Norris-Wine game, where we have to introduce non-sparse system of moves and therefore non-coherent orientation. So what we ended up doing is taking 4 moves. So we pair up the colorings. And there's, in some sense, we already, like the leitmotif is to use the symmetries and sort of exhaust all the possible, like try to get everything you can from the symmetries. And here, if we want to pair the colors in some way, the way we did it is this is just for flavor, it's not really something. In the hypercube, there's 4 directions, and we just this and whatever the 4 direction is, the 4 dimension is. So one pair of colorings is going to be, for example, these 2 colors are going to be paired up, and then maybe these 2 in the vertical one, and maybe these 2 in this direction, and then one other pair there. And we developed this symmetry, but now I have to just tell you for what do we do, because now we don't have a coherent orientation of the cube complex, and we have to build them up. I'll draw it here, let's say. So what happens is that inside the cube complex, you will have a lot every time. So squares in the complex correspond to ridges in the tessellation of the manifold, which are intersection of 2 facets. When the 2 facets that intersect there's good ridges when you don't have this phenomenon that you have adjacent facets on the same move, and they behave exactly like before. So this is good. But then you also have the bad behavior, where you get the moves that change. When you go from here, the vertex maybe is like this, but when I move, both are of change, not only this one has to change because it has to go in, but here also this one go in, and this one goes like this. And so there's a way to solve this, to define a map. So there's a very easy way to define a map to S1 from this, which we talked about, but there's for now, no obvious way to define a map to S1 from this square. And definitely there's no way to define a map from S1, from this square to S1, which has no critical points inside the square. So this looked counterintuitive. But what we did is we subdivide the square in some way, and we had a map. We define a map separately on all these triangles. So for example, in this triangle, the map just wants to go up because you're going up and up also in this direction. Here the map just wants to go right. Here the map just wants to go down. And here just wants to go left. So here we have a saddle points if we restrict to the two-dimensional cells in this square. But this is not terrible because when we are looking at the higher dimensional cubes, here this square will be part of another cube. Let's draw it in 3 dimensions because I cannot have this. And maybe here the arrows are not nice. They're like this. But since when we build this construction, we managed to have the bad ridges to be far away from each other, they don't interact with each other. And so here, for example, there's all arrows going up. And when you look at the link, you subdivide all the cubes. And when you look at the link, you do the same theory. You apply the same theory to this subdivision. And here you get the link of this. So inside the square, the link sees 2 points going out and 2 points going in. But in the 3-dimensional case, you see actually also an out ear and an out ear. And so the link is actually like this. No, in here. The arrows go in from below. Sorry. So the link is going to be something like this and also something like this. And so they are just segments. So I'll try and tell you about, I'll not tell you, I will list you some easy examples if you want to try this construction by yourself to familiarize with it. Maybe so in 3 dimensions. So if you take P3, which I told you was like this B pyramid, this pi pyramid, you can color it with 3 colors. And if you choose the trivial system of moves, and I mean, the number of states is very low, so you can try initial states until the whole orbit is nice. If you try the most obvious one first, then that one is the one that works. It's always the symmetry is this. And with the dodecahedron, the only way I can make it work is by doing this. So there's a coloring, there's a 6 coloring, which is not the most efficient one. You can do it with 4, but it's the most symmetric one. You can just color with the same color opposite facets. There's 12 facets, and you color each opposite pair with 1 color. You take a system of moves with 3 moves, which is not sparse. And you choose a symmetric So let's say, and then you find a fibrin on the manifold tessellated by this dodecahedron. So this maybe we'll call it exercises. Just if one wants to. Okay, and I think I will close here. Thank you.